Chapter 8. The Resolution Phase of Inflammation. The resolution phase of inflammation is the part of sequence in which the body stops treating the tissue as an active battlefield and begins converting that same tissue into a site of clearance, containment, and restoration. That description sounds simple, but the biology underneath it is exacting. Resolution is not the passive fading of inflammatory noise once the initial trigger becomes weaker. It is a coordinated phase change. The system has to stop further unnecessary recruitment, limit ongoing collateral damage, remove dead cells before they rupture into new inflammatory fuel, clear extracellular debris, normalize vascular permeability, restore barrier behavior, withdraw pain amplification that is no longer protective, and rebuild enough structural order that the tissue no longer presents itself as unfinished danger. Every one of those tasks requires signals, energy, timing, and substrate. That is why the resolution phase deserves to be treated as its own chapter rather than as the end note of inflammation. It is not the quiet part after the important work. It is the important work that determines whether the earlier phase leaves behind healing or persistence. This shift in phase changes the meaning of the inflammatory environment. During initiation, tissues become more permeable, more vascularly reactive, more chemically loud, and more permissive to immune traffic because the body is prioritizing access and force. During resolution, those same priorities must begin reversing without losing control of the site. The body cannot simply slam inflammatory activity off. It has to manage the handoff. Neutrophil-heavy recruitment must taper at the right time. Macrophages must become better finishers, not just continued participants in damage chemistry. Cytokine tone has to change from amplifying the event to containing it. Lipid mediator output has to shift from arachidonic acid-dominant initiation language toward pro-resolving instruction. Endothelial surfaces have to stop behaving like open emergency corridors. Epithelial and tissue barriers have to regain selectivity. The tissue is still active during this phase, but its activity is now aimed at ending the event intelligently rather than extending it by habit. One reason the resolution phase is so often missed is that it does not always look dramatic from the outside. Early inflammation announces itself through pain, swelling, heat, redness, restricted movement, fatigue, or measurable spikes in familiar inflammatory markers. Resolution is less theatrical. It appears as improved cleanup, reduced inappropriate recruitment, normalized permeability, fading pain sensitization, more efficient debris removal, and a gradual return of tissue control. But those quieter changes are not biologically secondary. They are what determine whether tissue can regain coherence. A wound can stop bleeding and still fail to resolve well. An infection can be controlled and still leave behind immune disorder if the cleanup phase remains poor. A joint can become less acutely swollen and still remain metabolically inflamed if dead cells, oxidized lipids, and extracellular debris are not cleared effectively. Resolution is therefore not defined by the disappearance of symptoms alone. It is defined by the successful completion of tissue-level tasks that make the disappearance of symptoms biologically trustworthy. At the center of this phase is a change in what cells are being asked to do. Early inflammation is built around access, detection, amplification, and immediate containment. Resolution is built around removal, restraint, and repair-compatible order. Neutrophils, while often necessary early, are not supposed to dominate indefinitely. Their continued arrival and continued presence become damaging if the site no longer requires acute force. Macrophages have to assume a more decisive role, especially through efferocytosis, the engulfment of apoptotic cells before those cells spill their contents and create fresh inflammatory provocation. This single task has enormous importance. If dead cells remain uncleared, the inflammatory site never receives the message that useful work has been completed. Debris remains visible. Damage remains legible to the immune system. The body keeps interpreting the area as active, unfinished business. The resolution phase succeeds only when cleanup becomes efficient enough that the tissue stops broadcasting emergency. This is where specialized pro-resolving mediators become indispensable. Without them, the body still knows how to start inflammation, but it loses much of the biochemical intelligence required to finish it well. Resolvins, protectins, marazins, and related mediator families help reduce ongoing neutrophil influx, improve macrophage-driven clearance, limit unnecessary tissue injury, and support the normalization of the local environment. These are not suppressive effects in the blunt sense. They are transition effects. They tell the tissue that further escalation is no longer the smartest move. They redirect effort away from force and toward completion. Because these mediators are derived from stored omega-3 substrate, the resolution phase also makes plain why membrane composition matters so much. A body cannot generate a strong resolution program from a membrane environment that never carried enough appropriate precursor material to begin with. The vascular side of this phase is just as important as the immune side. Early inflammation opens access. Resolution has to close it again without trapping unresolved damage inside the tissue. That means endothelial behavior must normalize. Permeability must decrease from emergency levels. Plasma leakage has to fall. Traffic signals that were encouraging cellular entry have to quiet down. Fluid balance has to begin restoring. If vascular behavior remains in the early phase state, tissue continues to swell, signaling continues to spread, and the local environment remains more permissive to repeated activation. In other words, the body keeps the door open after the relevant surge has passed. Resolution requires that the door begin closing at the same time cleanup becomes more effective. Without that synchronization, the tissue lives in a half-open state where incoming inflammatory pressure and outgoing debris clearance never fully match. Pain biology also changes during resolution, and this is often overlooked because pain is usually treated only as a symptom to manage rather than a signal to interpret. Early in inflammation, pain sensitization serves a protective purpose. It discourages loading of damaged tissue and marks the area as unsafe for normal behavior. But once useful protection has been achieved, continued pain amplification becomes a sign that the tissue has not completed its return to order. The nervous system remains informed that the site is still dangerous, and that continued message alters movement, stress response, sleep, mood, and systemic energy allocation. Resolution, therefore, has to include desensitization in the proper sequence. Pain does not simply vanish because time passed. It becomes less necessary because the tissue stops generating the inflammatory and structural evidence that justified elevated nociception in the first place. A body that cannot resolve well often becomes a body that cannot stop protecting tissues long after the relevant threat has diminished. Resolution is also metabolically expensive, which is why mitochondrial capacity and general energetic integrity matter so much here. Cleaning up after inflammation is not passive rest. Phagocytosis costs energy. Rebuilding membranes costs energy. Restoring junctions, re-establishing gradients, processing damaged components, and shifting cell phenotypes all cost energy. A tissue living under mitochondrial strain may still be able to launch inflammatory activation because activation can be driven by stored substrate release, stress signaling, and acute immune mobilization. But that same tissue may fail when it comes time to pay for the labor of closure. The result is one of the defining asymmetries of chronic inflammatory disease. The body still has enough force to begin, but not enough organized energy to finish. This is why the resolution phase cannot be treated as merely a signaling question. It is also a question of whether the tissue has the metabolic means to execute the work that the signals are trying to direct. Barrier restoration belongs to this phase for the same reason. Inflammation often begins by temporarily loosening normal control. That can be useful when access is necessary, but if barriers do not recover, the tissue remains vulnerable to new triggers while still trying to recover from old ones. Intestinal barriers that remain too permeable continue feeding immune-provoking material into the system. Epithelial barriers that remain open continue exposing tissues to unnecessary insult. Cellular membranes that remain oxidatively fragile continue generating danger chemistry and releasing signals that make neighboring cells interpret the area as unstable. The resolution phase has to reduce this constant re-triggering. It has to make the tissue harder to alarm once the acute need for alarm is gone. Otherwise, the body gets trapped in a loop where every attempt at completion is interrupted by the arrival of fresh evidence that the emergency is not over. This is why chronic inflammation is so often better described as failed resolution than as excessive initiation alone. Many chronically ill tissues are highly competent at starting. They release arachidonic acid. They generate eicosanoid cascades. They recruit. They amplify. They sensitize. What they do poorly is carry the event through efferocytosis, barrier restoration, vascular normalization, membrane repair, and immune de-escalation strongly enough that the site stops behaving as a site of threat. The resolution phase is the half of inflammation that has been missing from much of public and even clinical thinking, and without it the entire picture stays distorted. One keeps asking how to reduce inflammation when the deeper question is how to make inflammation finish. The answer is not simple silence, is successful sequence. That is the defining logic of this chapter. The resolution phase of inflammation is the body's method for ending inflammatory work without leaving behind a residue of danger. It depends on specialized mediators, cleanup-capable immune cells, restored vascular control, repaired barriers, sufficient energy, and membranes built from substrate that can support completion rather than only escalation. If that phase succeeds, tissue returns to order with minimal collateral damage. If it fails, the body remains suspended in a state of unfinished defense, where activation continues to recur because the environment never stopped looking like a problem. Resolution is therefore not the fade-out of inflammation. It is the disciplined biological achievement that determines whether inflammation becomes healing or becomes chronicity. Inflammation is a program with an end state. Inflammation is often described as if it were a force that simply rises when the body is threatened and falls when the threat disappears. That description is incomplete because it treats inflammation like a volume change rather than a program sequence. In reality, inflammation is a timed biological operation with defined phases, defined goals, and an intended end state. It begins by detecting disruption, shifts tissue into a defensive mode, recruits the necessary cellular machinery, contains damage or threat, clears what must be removed, and then transitions toward restoration. The end state is not merely less inflammation. The end state is recovered order. Vascular permeability returns toward baseline. Neutrophil-heavy recruitment stops. Macrophages clear apoptotic cells and debris. Pain amplification withdraws once protection is no longer needed. Barriers reform. Membranes stop broadcasting damage. Tissue stops presenting itself as an emergency zone. That is what completion looks like. This matters because a program is judged by whether it finishes, not merely by whether it starts correctly. A body that can initiate inflammation but cannot reach its end state is not exhibiting too much inflammation in the most meaningful sense. It is exhibiting incomplete inflammation. The difference is critical. If inflammation is seen only as force, the obvious response is suppression. If inflammation is seen as a program, then the more serious question becomes whether the program is moving through its full sequence. Has recruitment given way to clearance? Has activation given way to containment? Has tissue transitioned from damage control into repair-compatible stability? The pathological problem in many chronic conditions is not that the body still has inflammatory capacity. It is that the program keeps restarting or remains stalled before it reaches termination. The idea of an end state also explains why resolution is not passive. Programs do not complete themselves by drifting. They complete because later instructions become dominant. In inflammation, those later instructions include reduced neutrophil influx, improved erythrocytosis, normalization of vascular behavior, restoration of epithelial and endothelial boundaries, and the generation of specialized pro-resolving mediators from omega-3 derived substrate. Without those signals and those tasks, inflammation does not truly end. It only fluctuates in intensity. Tissue may look quieter for a time, while remaining structurally unfinished underneath. The real end state is not symptom reduction alone. It is the point at which the tissue no longer requires emergency logic to maintain control. Once inflammation is understood this way, chronic disease starts to look different. Chronic inflammation is what happens when the program loses its end state. The body still detects, it still recruits, it still amplifies, but no longer exits efficiently. Debris remains, barriers remain open, membranes remain unstable, immune cells remain in the wrong mode. Signaling remains biased toward continuation rather than completion. The system is not just inflamed, is stuck inside an unfinished biological script. That is why the goal should not be framed only as reducing inflammation. The deeper goal is restoring the body's ability to let inflammation arrive, do its work, and then terminate in a way that leaves tissue more ordered rather than chronically defended. Initiation, amplification, resolution. Inflammation is best understood as a sequence rather than a state. It begins with initiation, moves through amplification, and is supposed to end in resolution. Each phase has a different job, a different signal logic, and a different cost to the tissue. Problems arise when these phases are collapsed into one vague category called inflammation because the body does not treat them as interchangeable. Initiation exists to detect disruption and convert it into local action. Amplification exists to expand and coordinate that action so the problem can be contained effectively. Resolution exists to stop the continued use of force once force has done enough, clear what the inflammatory process has produced, and restore tissue conditions that make ordinary function possible again. If the first phase is missing, defense is weak. If the second is missing, defense is too small to contain the threat. If the third is missing, defense becomes chronic damage. The health of the system depends on movement through the whole sequence, not on the isolated strength of any one phase. Initiation is the moment the tissue decides that ordinary maintenance is no longer enough. Damage signals, microbial patterns, oxidative stress, mechanical disruption, or barrier breach activate receptors and membrane-associated enzymes. Arachidonic acid is released from phospholipids. Early eicosanoid production begins. Vascular tone changes. Permeability shifts. Platelets may become more active. Pain sensitivity rises. The tissue becomes chemically louder because attention and resources need to be redirected there. This phase is rapid by design. The body is not trying to deliberate endlessly. It is trying to mark a site as no longer ordinary and make sure the system notices. Initiation is therefore the phase of recognition and first response. It is where the inflammatory event is launched and where the local environment is altered enough to prepare for the next stage. Amplification follows because detection alone is not enough. Once the body has identified a meaningful problem, it has to scale the response to a level capable of containment. More immune cells are recruited. Cytokine signals intensify. Additional eicosanoids and related mediators are produced. Endothelial surfaces become more permissive to cellular traffic. Neutrophils and other early responders move into the tissue in larger numbers. Oxidative chemistry increases where microbial control or damage handling requires it. Pain signaling often becomes stronger, not because the body is malfunctioning, but because tissue must be protected behaviorally while the response is underway. Amplification is the phase of force multiplication. It expands the local inflammatory event into something large enough to matter. This is useful when proportional. It becomes dangerous when it continues after the tissue has already crossed the threshold of adequate response. Resolution is the phase that changes the meaning of everything that came before it. Without resolution, initiation and amplification remain open-ended. With resolution, they become part of a successful sequence. This phase reduces further neutrophil influx, improves macrophage-driven efferocytosis, clears apoptotic cells and extracellular debris, restores endothelial and epithelial control, reduces unnecessary pain sensitization, limits further collateral injury, and moves the tissue out of emergency logic. Specialized pro-resolving mediators derived from EPA and DHA become especially important here because they help provide the biochemical instructions for this handoff. Resolution is not the collapse of the inflammatory response from exhaustion. It is the active conversion of an inflammatory site into a recovering site. The tissue stops asking for more force and starts asking for cleanup, containment, and repair. The arrow between these phases matters because it shows direction. Initiation is supposed to lead to amplification when the problem requires escalation. Amplification is supposed to lead to resolution when continued escalation would cost more than it would protect. Chronic inflammatory disease often reflects failure of that directional movement. The body initiates correctly enough and amplifies powerfully enough, but the handoff into resolution is weak, delayed, incomplete, or repeatedly interrupted. The result is a tissue that keeps living in the first two phases. It remains recruited, sensitized, permeable, and chemically expensive because the third phase has not taken command strongly enough to finish the event. That is why the full sequence matters more than any single marker of inflammatory output. Healthy inflammation is not low inflammation. Healthy inflammation is inflammation that can move all the way through its own program and arrive at its end state instead of looping inside the middle. SPMs as the stop signal. Specialized pro-resolving mediators can be understood as the body's stop signal, but only if that phrase is understood precisely. They are not stop signals in the sense of shutting biology down, freezing immunity, or forcing silence onto tissue that still needs active defense. They are stop signals in the sense of telling the inflammatory program that further escalation is no longer the correct task. That distinction matters because the body does not need inflammation to disappear at random. It needs inflammation to stop expanding once the useful work of initiation and amplification has been done. SPMs provide part of that instruction. They help the tissue shift out of recruitment, permeability, collateral damage, and repeated alarm signaling, and into clearance, containment, and restoration. They do not just make inflammation quieter. They tell the system to stop doing the kind of work that belongs to the earlier phase. This is why the word signal is more accurate than the word suppressor. A suppressor reduces output whether or not the sequence has been completed. A stop signal changes what the system does next. In the presence of SPM activity, neutrophils are no longer called in excess to a site that has already received enough acute phase force. Macrophages are pushed toward efferocytosis and cleanup rather than continued inflammatory participation. Endothelial behavior begins moving away from emergency openness. Pain-promoting chemistry begins losing priority as tissue danger decreases. The inflammatory site stops behaving like a place that still needs more reinforcement and begins behaving like a place that needs to be cleared and rebuilt. That is a much more intelligent form of stopping than blunt inhibition. It preserves the logic of the sequence while ending its wasteful continuation. The stop signal role of SPMs is especially important because inflammation has a natural bias toward continuation once it is underway. Early mediators recruit cells, recruited cells generate more signals, oxidative chemistry damages more structure, and damaged structure creates fresh inflammatory evidence. Without an active signal telling the system that enough force has been applied, the body can remain trapped in recruitment and amplification. SPMs interrupt that loop. They do not deny that the loop was necessary at first. They terminate its dominance once the balance of cost and benefit has changed. That is why they belong to resolution biology rather than to generic anti-inflammatory thinking. They do not oppose inflammation as a category. They oppose the continued use of early-phase inflammatory logic after that logic has already done its job. Seen clearly, SPMs as the stop signal means they are part of the body's way of closing the inflammatory loop without leaving the site unfinished. They tell the tissue to stop calling for more force and start processing what force has already produced. They are the biochemical instruction that says enough recruitment, enough permeability, enough escalation, now clear, restore, and return to order. Without that signal, inflammation can remain chemically active long after its useful phase has passed. With it, the body gains a way to end defense intelligently rather than merely silence it. Why resolution is an active process? Resolution is an active process because the body does not return from inflammation to normal function by waiting. It returns by doing work. That work includes stopping further unnecessary immune recruitment, clearing apoptotic cells before they rupture into fresh inflammatory stimulus, removing extracellular debris, withdrawing pain sensitization that is no longer protective, restoring endothelial and epithelial control, rebuilding damaged membrane structure, and reestablishing the metabolic and signaling conditions that allow the tissue to stop presenting itself as a site of danger. None of that happens automatically just because the initial trigger has weakened or because inflammatory output has been partially reduced. The tissue has to be reorganized. The inflammatory site has to be dismantled. What was open has to be closed again. What was recruited has to be cleared. What was damaged has to be rebuilt. Resolution is active because order has to be reconstructed, not merely uncovered. This is one of the most important corrections to the old view of inflammation. For a long time, resolution was treated as a passive fade-out, as if the body simply ran out of inflammatory force and drifted back toward baseline once enough time had passed. That interpretation misses the biological labor involved. Neutrophils do not remove themselves efficiently without consequences if they are not recognized and cleared. Debris does not disappear harmlessly if it is left in tissue. Vascular permeability does not always tighten back to normal if the signaling environment remains stuck in emergency mode. Membranes damaged by oxidative and inflammatory stress do not quietly reset themselves. A tissue can become less dramatically inflamed on the surface while remaining biochemically unfinished underneath. Active resolution is what prevents that unfinished state from becoming chronic. It is the phase in which the body deliberately cleans up after its own defense. The immune system illustrates this clearly. Early inflammation depends heavily on recruitment and amplification, but those same mechanisms become harmful if they continue after acute needs have been met. Resolution requires an active shift in immune cell behavior. Macrophages, in particular, have to become effective finishers. They must increase efferocytosis, clear apoptotic cells and inflammatory remnants, and help change the local mediator environment away from continued escalation. This is not passive decline. It is a functional reprogramming of the inflammatory site. The body is changing the assignment from attack to cleanup. Without that reassignment, dead cells remain visible, oxidized material remains pro-inflammatory, and the tissue keeps interpreting itself as unfinished danger. Resolution is active because someone has to close the site, and biologically, that means cells have to do different work than they were doing at the height of the response. The lipid side of this process proves the same point. Specialized pro-resolving mediators are not passive indicators that inflammation is fading. They are active instructions derived from omega-3 substrate that help reduce further neutrophil influx, increase debris clearance, protect tissue from excess collateral injury, and restore a more stable local environment. These mediators do not emerge as a sign of exhaustion. They emerge as part of a later phase program. The body uses them to change what the tissue is being told to do. That is why omega-3 should be understood as resolution substrate rather than as a simple anti-inflammatory tool. The role of SBMs is not to let inflammation expire from neglect. Their role is to drive the transition from inflammatory action into inflammatory completion. Energy demand is another reason resolution must be active. Cleanup costs ADP. Membrane repair costs ADP. Restoring ion gradients, repairing junctions, phagocytosing debris, processing damaged cellular material, and rebuilding tissue architecture all cost ADP. A tissue under mitochondrial strain may still be able to launch inflammation because early inflammatory force can be driven by acute signaling, stress chemistry, and stored substrate mobilization. But completing the event requires sustained, organized work. If energy production is compromised, resolution weakens even if the tissue still has enough force to begin the response. This is one reason chronic inflammatory states often persist in metabolically unstable organisms. The body can afford to ignite. It cannot afford to finish. Active resolution therefore depends not only on the right signals, but on enough energetic capacity to carry out the repair those signals are calling for. Seen clearly, resolution is active because the body is not merely turning something off. Is changing tissue state, is moving from permeability to barrier control, from recruitment to clearance, from sensitization to normalized signaling, from damage handling to structural restoration. That requires instructions, cells capable of responding to those instructions, structural substrate that supports the later phase, and energy to carry the labor through. Passive language fails here because it makes healing sound easier than it is. Healing after inflammation is organized reconstruction. The body must actively finish what inflammation began, or the site remains stuck between defense and recovery, never fully dangerous enough to justify acute crisis, and never fully restored enough to return to normal. Chapter 9: Mechanisms of SBM Action. Specialized pro-resolving mediators matter because they do not merely exist as interesting downstream lipid products. They do things. They act through defined biological mechanisms that shift tissue out of inflammatory continuation and into controlled completion. That shift is the central subject of this chapter. If the previous chapters establish that SBMs are derived from EPA and DHA and belong to the resolution phase rather than to blunt suppression, this chapter has to explain how they actually achieve that effect inside living tissue. The answer is not that they simply make inflammation weaker. The answer is that they alter cellular behavior at several key control points at once. They reduce further inflammatory cell recruitment when additional recruitment would only increase collateral damage. They change macrophage behavior, so cleanup becomes more efficient. They improve the clearance of apoptotic cells and tissue debris before those materials can become new, inflammatory triggers. They help normalize vascular and epithelial function. They reduce the persistence of pain-promoting chemistry. They protect tissue while the body is transitioning out of the acute phase. In other words, SBMs are operational signals. They change the work the tissue is doing. The first major mechanism is receptor-mediated signaling. SBMs are not vague membrane effects acting only through bulk lipid incorporation. They bind to specific receptors or receptor systems and trigger downstream changes in immune behavior, inflammatory mediator production, and cellular movement. That matters because it means resolution is not just a passive drift created by substrate balance. It is directed instruction. Cells receive a new signal environment and begin carrying out different priorities. Neutrophils become less likely to continue moving into a site that has already received enough acute phase force. Macrophages become more likely to engulf dead cells and inflammatory debris. Endothelial behavior begins shifting away from facilitating high inflammatory traffic. Local cytokine tone changes. The tissue is not simply cooling off, it is being told to reassign effort away from continued escalation. A central mechanism of SBM action is the reduction of further neutrophil recruitment. Neutrophils are useful early because they provide rapid antimicrobial and damage response capacity, but they are expensive cells in tissue. They bring oxidative chemistry, proteolytic potential, and the capacity for collateral injury if they remain too long or keep arriving after the acute need for force has passed. SBMs help stop that continuation. They reduce signals that maintain excessive neutrophil trafficking and help interrupt the logic of perpetual reinforcement. This is critical because chronic inflammation often persists not only because old neutrophils remain, but because new neutrophils keep being invited into a site that no longer benefits from their presence. By lowering further influx without abolishing the initial ability to recruit when truly needed, SBMs help preserve host defense while ending wasteful extension of the inflammatory phase. The second major mechanism is the enhancement of efferocytosis and macrophage-driven clearance. This is one of the most important actions in the entire resolution program. Inflammation cannot end cleanly if apoptotic cells remain scattered through tissue or if inflammatory debris accumulates faster than it is removed. Dead cells left uncleared are not neutral. They become new sources of inflammatory provocation as membranes break down and intracellular contents spill into the extracellular environment. SBMs improve the ability of macrophages to recognize, engulf, and process these materials before they become additional danger signals. This is not a side effect of resolution. It is the center of it. A tissue stops behaving like an emergency zone when the visible evidence of the emergency is actually removed. SBMs help make that removal more efficient. A third mechanism is the reprogramming of macrophage behavior itself. Macrophages are not simple cells with one fixed inflammatory identity. They can participate in early inflammatory amplification, but they can also become the key finishers of the entire event. SBMs help drive that transition. They encourage macrophages to behave less like amplifiers of recruitment and more like coordinators of clearance, containment, and repair-compatible signaling. This is why the resolution phase depends so heavily on them. Chronic inflammation often reflects a site where macrophages remain present but fail to assume full finishing authority. The tissue is left in a chemically ambiguous state where danger has not been adequately cleared and further amplification remains too easy. SBMs help change that balance by making macrophages more effective at the later tasks that turn inflammation into healing rather than persistence. SBMs also act by limiting collateral tissue injury during the inflammatory transition. Acute inflammation is useful, but it is inherently dangerous because the same molecules and cells that defend tissue can also damage it if their activity remains excessive or poorly timed. Proteases, reactive oxygen species, inflammatory lipid mediators, and prolonged cellular congestion all threaten the tissue the body is supposedly trying to protect. SBMs do not eliminate defense. They narrow its waste. They help reduce the unnecessary continuation of damaging chemistry once the useful early phase work has been done. This is especially important in tissues where collateral injury is costly, such as the nervous system, vascular surfaces, epithelial barriers, and delicate organ microenvironments. In these settings, resolution has to be more than the disappearance of inflammatory markers. It has to include preservation of the tissue itself while the response is being wound down. Another major mechanism is the restoration of barrier and vascular control. Early inflammation often requires increased vascular permeability and greater access for plasma proteins and immune cells. That is useful during initiation and amplification, but if permeability remains elevated, tissue stays metabolically and immunologically open. Fluid continues to shift abnormally. Inflammatory signals continue to spread. Cellular traffic remains too permissive. SBMs help reverse that state. They support the transition back toward controlled endothelial behavior and more selective tissue boundaries. This is crucial because inflammation cannot be considered resolved while the tissue remains physically open to repeated provocation. Resolution requires the body to reduce access at the same time it increases cleanup. SBMs are part of the signaling environment that makes this coordinated closing possible. Pain modulation is another important mechanism. Pain during early inflammation often has clear biological purpose. It reduces movement, changes tissue loading, and keeps attention focused on the damaged area. But once the useful protective phase has passed, continued nociceptive amplification becomes part of the pathology. SPMs help reduce that persistence. They do not simply numb tissue in a crude way. They help remove the inflammatory conditions that keep pain signaling justified and can directly influence mediator systems that support ongoing hypersensitivity. This matters because chronic inflammatory pain is often not just a sensory problem. It is evidence that the tissue continues to behave as though danger remains active. By helping end the inflammatory conditions that sustain that interpretation, SPMs help withdraw protective pain once it is no longer biologically necessary. SPMs also act by influencing the broader mediator environment. One of the major problems in chronic inflammation is that the tissue remains dominated by early-phase signaling chemistry. Eicosanoid cascades continue to shape the site as though more recruitment and more amplification are still appropriate. SPMs change that mediator balance. They do not merely subtract inflammatory mediators. They add a different instructional class that tells the system to stop repeating the same early logic. This is why they should not be described as passive offsets. They actively compete at the level of tissue, meaning the site receives a new message about what phase it is in, and that changes what cells interpret as necessary. An important feature running through all of these mechanisms is that SPMs preserve defense while ending excess continuation. That is what makes them so different from blunt suppression. They do not create a biologically naive tissue. They create a tissue capable of finishing. The body still responds to genuine disruption. It still contains threats. It still uses inflammatory force where force is needed. But once sufficient force has been applied, SPMs help shut the gate on further escalation and turn the system toward removal, preservation, and rebuilding. That makes them mechanistically elegant. They solve the real problem in many chronic inflammatory states, which is not the existence of immune competence, but the lack of immune closure. This chapter, therefore, makes one core point. The mechanisms of SPM action all converge on phase transition. They reduce further neutrophil influx, enhance efferocytosis, shift macrophages into cleanup modes, limit collateral damage, restore barrier behavior, reduce persistent pain signaling, and alter the mediator environment so tissue stops acting as though escalation is still required. Every one of those actions helps answer the same problem. How does the body stop an inflammatory event without leaving the tissue unfinished? SPMs are the answer because they do not simply oppose inflammation. They organize its ending. If you want, I'll continue with the first subsection under stopping neutrophil infiltration. Stopping neutrophil infiltration is one of the most important ways specialized pro-resolving mediators change the direction of inflammation. Neutrophils are essential early responders. They arrive quickly, move aggressively into damaged or infected tissue, release oxidants, proteases, antimicrobial factors, and signaling molecules, and help establish the first wave of acute containment. That role is useful at the beginning because speed matters. But the same features that make neutrophils valuable early also make them dangerous if their entry continues after the acute need for force has passed. Every additional wave of neutrophil infiltration increases oxidative burden, proteolytic pressure, membrane injury, endothelial disruption, and the amount of cellular debris that must later be cleared. A tissue cannot resolve while it is still being continuously restocked with cells built for early-phase damage control. Resolution, therefore, requires not only that existing inflammatory material be cleaned up, but that new neutrophils stop being invited in excess. This is why stopping infiltration is not the same thing as erasing immunity. The body is not trying to prevent neutrophils from ever arriving. It is trying to stop recruiting more of them once enough have already arrived to do the necessary early work. That is a phased decision. Early inflammatory signals encourage neutrophil rolling, adhesion, extravasation, and migration into the tissue through changes in endothelial behavior, chemokine gradients, lipid mediator output, and local vascular dynamics. SPMs help reverse that logic. They reduce the signaling conditions that keep drawing neutrophils inward. They make the tissue less chemically attractive to continued recruitment and less structurally permissive to endless inflammatory traffic. This is not suppression in the blunt sense. It is a controlled withdrawal of the invitation. The importance of this becomes obvious when chronic inflammation is viewed from the tissue level. A chronically inflamed site often remains metabolically expensive because neutrophil-heavy logic never fully shuts off. Even if individual cells die and are cleared, new cells keep entering. That means fresh oxidants, fresh proteases, fresh membrane damage, and fresh inflammatory residue continue appearing faster than the tissue can finish cleaning up the last round. The site never stops looking active because it never stops receiving new acute phase machinery. In that setting, stopping neutrophil infiltration is not a minor adjustment. It is one of the core conditions required for resolution to even begin. Cleanup can only dominate if new damage-producing cellular input begins to fall. This is also where the elegance of SBM biology becomes clear. Specialized pro-resolving mediators do not stop neutrophils by paralyzing the immune system. They stop the continuation of neutrophil entry by changing the local meaning of the tissue environment. The site is no longer treated as one that needs more escalation. Endothelial signals become less recruitment-oriented. Chemotactic pull declines. The inflammatory field starts shifting from a zone of entry toward a zone of processing. This allows existing neutrophils to undergo apoptosis and be cleared by macrophages without being constantly replaced. It is a handoff mechanism. The tissue stops prioritizing arrival and starts prioritizing removal. That handoff matters because neutrophils are biologically short-lived. In a well-sequenced inflammatory response, they arrive, do acute work, and then are removed before they become a major source of secondary tissue injury. If infiltration continues too long, however, the sheer turnover of dying neutrophils becomes part of the pathology. Apoptotic cells accumulate. Clearance systems become overloaded. If efferocytosis cannot keep pace, those cells break down and spill intracellular contents into the extracellular environment, generating more inflammatory stimulus and reinforcing the impression that the site remains dangerous. Stopping neutrophil infiltration therefore protects the tissue in two ways at once. It reduces immediate collateral damage from new arrivals, and it lowers the future cleanup burden that would otherwise keep the site trapped in inflammatory continuation. Seen clearly, stopping neutrophil infiltration is one of the first true signs that inflammation is entering resolution rather than merely fluctuating in intensity. The tissue is no longer calling for reinforcement. It is beginning to act as though the acute emergency has been contained well enough that more force would now cost more than it would protect. That is exactly the kind of decision specialized pro-resolving mediators help enforce. They do not deny the need for early neutrophil action. They mark the point at which further neutrophil entry stops serving recovery and starts interfering with it. Without that shift, inflammation remains an open door. With it, the body gains the chance to move from repeated recruitment into actual completion. Enhancing macrophage cleanup, efferocytosis. Enhancing macrophage cleanup, especially through efferocytosis, is one of the central mechanisms by which resolution becomes real rather than theoretical. Efferocytosis refers to the recognition, engulfment, and processing of apoptotic cells before they lose membrane integrity and spill their contents into the surrounding tissue. That function sounds technical, but it sits close to the heart of whether inflammation ends cleanly or persists. A tissue cannot resolve simply because recruitment slows down. It has to remove the physical remains of the inflammatory event. Neutrophils that have done their work must be cleared. Damaged cellular fragments must be cleared. Oxidized membrane material, extracellular debris, and the remnants of local tissue injury must be cleared. If that does not happen, the inflammatory site remains full of biochemical evidence that the emergency is still active. Macrophages are the major finishers of this phase, and efferocytosis is one of the main ways they turn inflammatory terrain into recoverable terrain. This is why macrophages should not be understood only as inflammatory cells. Early in the sequence, they can participate in cytokine production, immune coordination, and local amplification, but their deeper importance in resolution comes from their ability to change roles. Once acute force has done enough, macrophages have to become cleaners, sorters, and stabilizers. They identify apoptotic cells through altered surface signals, engulf them without allowing those cells to rupture outwardly, and then process what they have taken up in a way that reduces rather than amplifies further inflammatory provocation. This is a remarkably intelligent biological maneuver. The body is not merely removing waste. It is removing it quietly. The contents of dying cells are contained rather than scattered. Their presence stops serving as open evidence of tissue danger. The tissue begins to look less inflamed because the material that justified ongoing inflammatory interpretation is physically disappearing. Specialized pro-resolving mediators help enhance this process by improving the efficiency and priority of macrophage cleanup. They do not just reduce inflammatory noise in the abstract. They make macrophages better at the actual labor of ending an inflammatory event. This matters because unresolved inflammation often reflects not only too much initiation, but too little successful removal of what initiation produced. A site may contain large numbers of apoptotic neutrophils, oxidized membrane remnants, damaged extracellular material, and fragments of injured cells. If macrophages clear these efficiently, the tissue can move toward stability. If they do not, those materials remain in place long enough to become new sources of inflammatory stimulus. Efferocytosis is therefore not a cleanup detail added after the main event. It is one of the main events in the transition from active inflammation to restored control. The word quietly matters here. When apoptotic cells are not cleared in time, they can progress into secondary necrosis, losing membrane integrity and releasing intracellular contents into the extracellular environment. At that point, what could have been removed silently becomes a new inflammatory trigger. Damage-associated molecular patterns spread. Oxidized lipids and proteins remain exposed. Proteases and other degradative contents escape. Nearby cells interpret this as ongoing disturbance. An inflammatory program is fed another round of evidence that the site is still dangerous. Efficient efferocytosis prevents that conversion. It reduces the chance that yesterday's inflammatory cells become today's inflammatory fuel. In this sense, macrophage cleanup is not only restorative, it is protective against reinitiation. This mechanism is one reason chronic inflammation so often looks like a failure of finishing rather than a failure of starting. Many chronically inflamed tissues still recruit well. They still produce cytokines, eicosanoids, and vascular changes. What they do poorly is clear the aftermath with enough speed and intelligence to break the loop. Macrophages remain present, but they are either overwhelmed, poorly instructed, metabolically strained, or held in phenotypes that favor participation in inflammatory signaling more than completion of inflammatory work. The site remains crowded with cellular remnants and oxidized structural debris. Even if new triggers stopped arriving, the internal residue would still keep the tissue looking unfinished. Enhancing macrophage cleanup through SPM biology changes that situation by making the tissue better at physically removing the reasons it continues to appear inflamed. Macrophage cleanup also changes the mediator environment in a self-reinforcing way. Successful efferocytosis does not merely subtract debris. It influences what macrophages do next. As they engulf apoptotic cells and process inflammatory remnants, they shift further away from aggressive inflammatory amplification and further toward repair-compatible signaling, restraint, and tissue support. This means cleanup is not just a terminal act. It reshapes the character of the inflammatory site. A macrophage that is cleaning effectively is participating in resolution at multiple levels at once. It reduces visible inflammatory material, lowers the chance of secondary inflammatory triggering, and helps move the local signal environment toward completion rather than continuation. Efferocytosis therefore acts both as sanitation and as instruction. This is especially important in tissues where inflammatory debris is costly. In the vascular system, retained inflammatory material can prolong endothelial dysfunction and keep permeability or reactivity elevated. In joints, retained debris can maintain pain and immune activation even after the original acute insult has passed. In neural tissue, poor clearance can be especially damaging because even modest structural disorder can alter signaling precision and microglial behavior. In barrier tissues such as the intestine, unresolved cellular debris can combine with ongoing exposure to luminal triggers and make the site exceptionally difficult to calm. In all of these contexts, improving macrophage cleanup is not optional if the body is to move beyond chronic inflammatory repetition. The tissue has to become physically cleaner before it can become biologically quieter. Seen clearly, enhancing macrophage cleanup through efferocytosis is one of the most concrete expressions of what resolution actually means. It means the inflammatory site is no longer defined by ongoing arrival of force, but by competent removal of what that force left behind. It means the body is not simply asking inflammatory cells to disappear. It is actively collecting them, processing them, and using that process to transition the tissue toward repair. This is why SPMs matter so much. They help make macrophages better closers. They help transform an inflamed environment from one that remains crowded with the residue of damage into one that can finally stop looking like a problem. Without efferocytosis, inflammation lingers because the evidence of inflammation remains. With it, the body gains one of the main mechanisms by which defense can end without leaving disorder in its wake. Clearing cellular debris. Clearing cellular debris is one of the most decisive tasks in the resolution phase because inflammation cannot end in any meaningful way while the tissue remains physically full of evidence that damage is still present. Cellular debris is not inert clutter. It includes apoptotic cells that have not yet been removed, fragments of damaged membranes, oxidized lipids, denatured proteins, extracellular matrix remnants, microbial remains where applicable, and the biochemical residue left behind by neutrophils, macrophages, and stressed tissue cells. As long as this material remains in place, the inflammatory site continues to look dangerous to the immune system. Receptors keep encountering signals associated with disruption. Oxidative chemistry remains easier to sustain. Additional immune recruitment remains easier to justify. The body therefore cannot move fully into repair while the local environment still resembles a partially dismantled battlefield. Resolution requires the tissue to become physically cleaner, not just chemically quieter. This is why debris clearance is not a cosmetic finishing step after the real inflammatory work is over. It is part of the real work. The inflammatory response itself creates waste. Neutrophils arrive, carry out acute functions, and then die. Damaged host cells must be removed. Oxidized phospholipids and fragmented membrane components accumulate. Proteases, nucleic acid fragments, and disrupted structural proteins remain in the extracellular space. If these materials are left where they fell, they become a new layer of inflammatory stimulus. Even when they are no longer part of the original threat, they continue to signal that the tissue is unsettled, injured, and biochemically unsafe. The body then keeps behaving as though the inflammatory phase is still needed because the tissue keeps presenting unresolved evidence that something remains unfinished. Debris clearance is what breaks that illusion and allows the site to transition out of emergency mode. Macrophages are central to this process, but the mechanism extends beyond simple phagocytosis of whole apoptotic cells. The tissue has to collect and process a wide range of damaged material. Membrane remnants have to be internalized and degraded. Oxidized lipid fragments have to be removed before they continue interfering with nearby membranes or serving as danger signals. Protein debris has to be cleared so it does not remain as extracellular irritant. In some cases, microbial fragments or remnants of damaged barrier contents also have to be managed. The site must be stripped of inflammatory leftovers with enough efficiency that the surrounding cells stop reading the local environment as open damage. This is one reason specialized pro-resolving mediators are so important. They do not only reduce future recruitment, they help improve the tissue's capacity to process what the previous phase already produced. The importance of this becomes even clearer when debris is not cleared well. If apoptotic cells remain too long, they lose membrane integrity and spill intracellular contents outward. If oxidized membrane fragments remain in tissue, they continue exposing surrounding cells to reactive breakdown products and distorted lipid signals. If extracellular protein debris remains lodged in the tissue matrix, local immune cells continue encountering structural evidence of injury. Each of these failures turns residue into reactivation. The tissue does not move forward because the remains of the last inflammatory cycle become fuel for the next one. This is one of the central reasons chronic inflammation can persist even after the original trigger has weakened. The site is still full of material that tells the body the job is not done. Debris clearance also reduces collateral damage indirectly by lowering the need for continued inflammatory force. A site that remains crowded with damaged cellular material continues requiring surveillance, continued phagocytic attention, and continued chemical defense. A site that has been cleaned effectively no longer justifies the same level of inflammatory mobilization. This is one of the most practical meanings of resolution. The body can stand down because the environment has changed. The visible and molecular signs of emergency are being removed. Once that happens, vascular permeability can normalize more safely, pain sensitization can start withdrawing, immune recruitment can decline, and tissue repair can proceed without being constantly interrupted by the residue of previous inflammatory activity. This is especially important in tissues where debris is costly. In joints, retained debris can sustain synovial irritation and pain long after the initial insult. In vascular tissues, retained cellular remnants can keep endothelial surfaces reactive and dysfunctional. In the nervous system, even modest accumulation of inflammatory residue can distort signaling and keep local immune cells in an activated state. In the gut, poor debris clearance can interact with ongoing barrier stress and continuous luminal exposure to make local resolution extremely difficult. In each case, the principle is the same. The tissue cannot fully recover while it is still carrying the remains of unresolved inflammation inside itself. Seeing clearly, clearing cellular debris is one of the ways the body converts an inflammatory site from a place of active danger into a place where repair becomes possible. It is not enough to stop new inflammatory cells from arriving. The tissue must also remove what those cells and the original injury have left behind. Until that happens, the local environment continues to advertise unfinished damage. Effective resolution therefore depends on cleanup that is both efficient and quiet. The body has to remove the physical residue of inflammation before it can truly stop behaving inflamed. Promoting tissue repair and regeneration. Promoting tissue repair and regeneration is one of the clearest signs that inflammation has truly entered its later phase, because repair only becomes possible when the body stops spending most of its resources on recruitment and containment. Early inflammation is designed to control disruption. It opens access, mobilizes force, and marks the tissue as a priority zone. But tissue cannot remain in that state and heal at the same time. Repair requires a different operating environment. Cellular traffic has to become more selective. Debris has to be cleared well enough that new structure is not being laid down into biochemical disorder. Oxidative and proteolytic pressure has to fall. Macrophages and surrounding cells have to shift away from destructive urgency and toward constructive work. Blood flow has to remain sufficient for rebuilding without remaining in a state of inflammatory excess. In that sense, repair is not what happens after inflammation disappears. Repair is what begins when inflammatory logic is successfully reprogrammed into restoration logic. This is why specialized pro-resolving mediators matter so much in tissue recovery. They do not simply make inflammation smaller. They help create the conditions under which rebuilding can occur without being constantly interrupted by fresh inflammatory damage. By reducing continued neutrophil recruitment, enhancing macrophage cleanup, limiting collateral injury, and changing the local mediator environment, SPMs make the tissue less dominated by emergency chemistry and more capable of restoration. That shift is essential because regeneration and repair require structural coherence. Cells cannot rebuild junctions, restore extracellular matrix organization, normalize membrane behavior, and reestablish communication across the tissue if the site remains chemically loud and physically cluttered with unresolved damage. SPMs help clear the ground so regeneration is not forced to compete with an unfinished inflammatory battlefield. Macrophages are central to this transition. Once they move into effective cleanup modes, they do more than remove waste. They begin shaping the tissue environment in a way that supports reconstruction. A site that has undergone successful efferocytosis and debris clearance stops broadcasting the same level of threat. That alone changes what neighboring cells do. Epithelial cells can begin restoring barrier structure. Endothelial surfaces can begin tightening control. Fibroblasts and other local structural cells can participate in rebuilding without being continuously driven by inflammatory distortion. The tissue becomes more orderly, and once order begins returning, regenerative work becomes more efficient because it is not constantly being overruled by persistent alarm signaling. This is one of the key principles of resolution biology. Cleanup and repair are not separate events. Cleanup is part of what makes repair biologically possible. Tissue repair also depends on the reduction of unnecessary collateral damage. A site under prolonged inflammatory escalation is continuously exposed to oxidants, proteases, membrane injury, vascular leak, and signaling excess. Even if the original insult has been contained, that ongoing chemistry keeps injuring the same tissue the body is trying to save. Regeneration cannot outrun repeated self-damage forever. The system has to stop destroying structure faster than it rebuilds it. This is another way SPMs promote repair. They help reduce the continuation of inflammatory force once that force is no longer proportionate to need. The tissue then has a chance to stabilize. Stabilization is the beginning of regeneration because cells can only rebuild effectively when the environment stops behaving as though it is still under attack. Barrier restoration is one of the most practical expressions of this process. In epithelial tissues, endothelial tissues, gut lining, skin, and other surfaces that define biological compartments, repair means more than replacing damaged cells. It means restoring selective control. A barrier that heals poorly continues allowing inappropriate exposure, continued immune activation, and repeated disruption of local structure. A barrier that heals well stops feeding the inflammatory loop. SPM-supported resolution helps this happen by lowering ongoing inflammatory pressure and supporting the phase transition required for cells to re-establish junctions, restore surface integrity, and reduce unnecessary permeability. Repair, therefore, includes reasserting boundaries. The tissue becomes a better barrier again, and by becoming a better barrier, it also becomes harder to re-injure through the same unresolved pathways. Energy remains a major constraint throughout this phase. Tissue repair is expensive. Membranes have to be rebuilt. Proteins have to be synthesized or reorganized. Junctions have to be restored. Extracellular matrix may need remodeling. Ion gradients must be maintained while damaged structures are replaced. A tissue that lacks energetic capacity may still enter inflammatory activation, but it will struggle to complete the slower and more organized labor of regeneration. This is one reason chronic inflammatory illness so often includes poor healing even when inflammatory activity is obvious. The body still has enough chemistry to defend. It does not have enough organized energy to rebuild well. Repair is therefore not just a signaling event. It is a metabolic commitment. The resolution phase promotes regeneration partly by reducing the wasteful energy drain of chronic inflammatory continuation so that tissue resources can be redirected toward reconstruction. The word regeneration has to be used carefully because not all tissues regenerate to the same degree, and not all repair restores original structure perfectly. Some tissues rebuild with remarkable fidelity. Others repair more by stabilization, compensation, or scar formation. But in all cases, the principle remains the same. The body can only move toward its best available form of restoration when inflammation has been sufficiently completed that rebuilding is no longer being sabotaged by continued recruitment, continued debris accumulation, and continued structural instability. Resolution does not guarantee perfect regeneration. It creates the conditions in which the highest level of recovery available to that tissue becomes possible. Seen clearly, promoting tissue repair and regeneration is one of the reasons the resolution phase should never be confused with simple anti-inflammatory suppression. Suppression can reduce visible inflammatory output without creating real rebuilding conditions. Resolution, by contrast, changes the tissue state in a way that allows restoration to begin. It reduces unnecessary continuation, improves cleanup, protects structure from further collateral injury, and reorients cellular behavior toward repair-compatible work. That is why SPMs and the broader resolution program matter so much. They do not merely help inflammation stop. They help the tissue become healable again.